Okay, great. Excellent, thank you. All right, so today what we're going to do primarily is talk about finitely generated abelian groups, which are a topic that are objects which come up all over the place in number theory. Before I start, though, a couple of comments. First, one student requested that the homework not be due on Wednesday. So do you guys have any remarks about that? Is Wednesday fine for you, or is Wednesday terrible? There's a student who suggested not having homework due on Wednesday. It's fine. I don't really know why. Okay.
I'd rather have something else.
Such as what would be better for you?
Either way, Monday or Friday.
Okay, let's just take a quick survey. So, for which person is Monday really bad?
I work through Monday.
Okay, for who is Friday really bad? And for who is Wednesday really bad? Okay, so Friday would be good. Okay, so let's change the homework so it's due on Friday. Okay?
Is this homework still due on Wednesday?
You can make it due on Friday, actually. So homework will now be due on Friday. I'd only chosen Wednesday before because I assumed that a lot of other classes would make homework due on Friday, and therefore Wednesday would be better for you. So you on Fridays.
I believe every teacher thought that.
Yeah, and they all chose Wednesday. Some sort of funny game. Okay. Another remark. Yeah.
Randomized.
Yeah, I should have just chosen a So another remark is if you email me some question that's a fairly general question about the course or math involving the course, I'm very likely to reply and CC the response to the mailing list for the course. So if you specifically don't want the response to go to the mailing list, you should say so, because the default is that it will go to the mailing list. Okay, second thing. Third, as I mentioned before, Trevor Arnold will be teaching this course all of next week. And what he'll be talking about is Noetherian rings, number fields, and rings of algebraic integers, and some abstract properties they have, which make them Dedekind domains. And I think he'll also talk about some things you can prove that Dedekind domains satisfy, some properties they have. Okay, so today's about finitely generated abelian groups and the Smith normal form. And we'll see, if I finish that, then we'll talk about Noetherian rings a little bit. So first, some notation. So these are the integers, and z mod nz is the integers modulo n, which has representatives 0, 1, through n minus 1, and where arithmetic is mod n. Some people will denote this by z sub n, but number theorists won't do that, because if n is a prime, then that's the same notation as used for the p-adic numbers, so it's very confusing. Some number theorists will write z slash n, but that's also confusing and bad because this could be confused with z adjoined 1 over n. So this, though, a very heavy notation, is the typical one that's used by most number theorists for the integers modulo n, which is kind of a prototypical example of a cyclic group of order n. So what we'll be concerned with today is finitely generated abelian groups. So an abelian group is a group that is commutative, and finitely generated means there's some finite list of elements of the group, so that every element of the group can be written in terms of that finite list. And the reason that I'm just going to say a few very precise things about finitely generated abelian groups that in particular allow you to do some computations with them is that they just come up so much in number theory. So they're very popular in number theory. In this course. For example, we'll consider class groups of number fields, and they are examples of finite abelian groups. we'll consider unit groups. So these are finitely generated. They're not finite, they're finitely generated. An example of a unit group is you take, for example, z adjoin 1 plus root 5 over 2, and then inside of there you can find an element that is a unit, that is, it's invertible in here, and it has infinite order. So in this case, the unit group is plus or minus 1 cross an infinite cyclic group. That's an example. And it turns out we'll prove a general structure theorem which says that if you take any number field at all, so any finite extension of the rationals, then consider inside of it the ring of integers, that is, all elements of the number field that satisfy a monic polynomial with integer coefficients, that the unit group, that is the set of elements U in the ring, so the unit group, the set of U in the ring, they're invertible, so U is invertible. This is a group that has, it's a product of R plus S minus 1 copies of Z, where R and S are the number of real and complex conjugate embeddings of the number field into the complex numbers. And it's a product of that free thing plus the torsion subgroup. So there's a very precise structure theorem for the unit group. And again, it's an example of a finitely generated distributed group. Another sort of more boring example is if you take the ring of integers OK in a number field, again, this OK being the set of all elements in the number field that satisfy a monic irreducible polynomial with integer coefficients. The additive group of this is a finitely generated abelian group. Another example, which we may encounter at the end of the course, if you consider an elliptic curve, E, here, this is a set of solutions to an equation y squared equals x cubed plus ax plus b, plus one additional point in infinity. So it's really a projective curve that is determined by taking the projective closure of the affine curve given by this equation. Then if A and B are both elements of a numbered field K, then the Mordell-Bay theorem says that the set of all solutions on this elliptic curve along with this one extra point in infinity has a natural group structure, and that group is a finitely generated abelian group. So these are all examples of finitely generated abelian groups that come up in number 3. And just to make sure I give you at least one open problem today, if you consider the case when K is the rational numbers, the possibilities for these groups have been very well studied. So here's an open problem. Is the number of generators for E of Q unbounded as you vary over all possible elliptic curves over Q?
So that number is just the rank of the curve, right?
That's exactly right. Yes, that it is unbounded.
And they sort of have large numbers of calculations that they...
I think what is the current rank? Noam Elke's recently established the current rank after two people at NSA found, I think, a curve of rank 24 and maybe 6 years ago, and then a few months ago, Noam Elke's found one, I think, of rank 28, maybe 29. And that's the biggest that's ever been found. So there's a specific curve you can write down and the number of generators is at least 28 for that curve, and no Melky is found. So you have a bunch of objects. If you look at a random curve, it's very likely that the number of generators is either 0 or 1. It's actually very hard to find examples where it's more than 2 or 3. And there's an example where it's greater than or equal to 28. So you have all these objects, and occasionally have some that are this number attached to them, namely the rank, that is the number of generators. By the way, I'm ignoring the torsion subgroup, so let's put slash tor here. That means quotient out by the torsion subgroup. So the number of generators for one example is 28. So you have all these objects, and amazingly, the standard conjecture is that the number of generators can be arbitrarily large. There should be some elliptic curve out there with rank 100 or 1,000 or something else, but nobody has any idea how to prove it.
Well, when you say unbounded, like there might not be one of rank 100. Like, is there a conjecture that every number is hit, or just
that's what the expectation is? Yeah. I mean, it would be something where you'd have a certain proportion. Well, not proportion. It would be 0% of curves having rank 2 or bigger, but you probably have infinitely many of every rank. That would be the most natural thing to expect in present. If you asked people 50 years ago, they would have thought the opposite, that there are only finitely many ranks that occur. But nowadays, I think that every rank occurs infinitely often, usually. That's what most people will say. Yes?
Just a question of the notation. The EK is a finitely generated abelian group?
Yes. So this notation means the set of solutions to this equation.
Given an A and B?
Yes, for a fixed A and B. So I'll write E sub A comma B everywhere. So given an A and B, you have a fixed one particular elliptic curve, and then you consider all pairs x comma y in k cross k that satisfy the equation y squared equals x cubed plus ax plus b, along with one extra point that can be thought of as being on infinity in the projective plane. Okay? All right, so these are all examples of finitely generated abelian groups, and therefore you definitely want to understand the basics of finitely generated abelian groups. So let's return to that. So the first, actually kind of hard thing to prove about finitely generated abelian groups, so G here is a finitely generated abelian group, is that if you consider a subgroup of G, H, if G is finitely generated, then so is H. So proposition G finitely generated implies H is finitely generated. And this isn't easy to prove. So what you do is you establish the basic theory of Noetherian rings and modules, and then this is an immediate consequence of that. And that will be done efficiently next time. So it follows from knowing what the word Noetherian means. In other words, this fits into a much nice general theory. So I won't prove this. Now, it's just something that will be immediately implied by what will happen during the next lecture. So just believe that for the rest of the lecture, if you don't already know. If you have a finitely generated abelian group, then any subgroup is automatically finitely generated. By the way, is this true if the group isn't abelian? Is any subgroup of a finitely generated group finitely generated?
No.
Give a counterexample. Or at least say something.
Basically, if you have a free group on 2 elements, we can actually generate an infinite free group within that.
You mean infinitely generated?
Infinitely generated free group, yeah.
Cool. Great. So thanks, James. So this isn't true if you don't assume that these are abelian. So everywhere these are finitely generated abelian groups. All right, so that's the first observation. The next one is you can take any finitely generated abelian group and you can write it as a quotient of 2 free finitely generated abelian groups. So as always, G is a finitely generated abelian group. So there is a way to write G as G isomorphic to L1 modulo L2, where L1 is isomorphic to z to the n, and L2 is isomorphic to z to the n. There's some integers n and m. And actually, we won't need that that L2 is free, since that's a little more work. So I'll just write that L2 is finitely generated. Actually, no. Let's. Oh, it's true. I'm going to prove something slightly weaker, which is enough for this. So let me write the actually slightly weaker statement of the proof. This is true, but it's a little hard to prove directly on what we already know. So what I'll prove is this. There's a sequence like that. In other words, we're here at L1 and L2 are z to the n and z to the m. The only difference here is I'm not assuming, in this notation, this sort of assumes that L2 is contained in L1. That's not at all necessary for anything we're going to do. So really all I mean is there exist two free abelian groups of finite rank so that the quotient, some map between them, is Rg. Okay, and then to prove this, it's easy. G is by assumption finitely generated by G1 through Gn. So just let L1 be z to the n, and then send each of the standard basis vectors for z to the n to G1 through Gn. Then the kernel of the resulting homomorphism, and it is a homomorphism because this is free, the kernel of the resulting homomorphism is an abelian subgroup of L1, so by the proposition I just stated, it's finitely generated by, say, m things, h1 through hm. And so just take z to the m here and map each of the standard basis vectors to h1 through hm. And now you've presented G as the quotient of 1 z to the n by a z to the m. And a map, as you know from probably teaching linear algebra or taking it, from z to the m to z to the n, you can represent that by a matrix. So we have a homomorphism phi here. Represent the homomorphism phi by a matrix. And it actually won't matter for what we're going to do too much about whether you view this as a matrix acting from the left or the right or whatever. But to be concrete, I'll view A as acting from the left on column vectors. And this is just exactly like in any linear algebra course. The map, this matrix A, has the columns, the images of the standard basis vectors under phi. So phi of E1 through phi of E. So it's a matrix, and the co-kernel of this matrix, that is the image, or codomain modulo the image, is isomorphic to G. So co-kernel is isomorphic to G. And now what I'm going to do is show you how to take any matrix like this and transform it via a sequence of transformations that all they're doing is changing the basis of each of these over Z, and you'll arrive at a new matrix, which is in what's called Smith normal form. And the nice thing is that a matrix in Smith normal form, you can tell exactly what the structure of the co-kernel is. So we'll be able to, in a sort of natural way, see what the structure of any finitely generated abelian group looks like.
Can you say what the co-kernel is again?
Yes, sure. If you have any homomorphism at all of abelian groups, from say, I don't know, m to n to n is a homomorphism of abelian groups, then and I'll denote it by psi here, then the co-kernel of psi is the abelian group, which is n modulo the image is psi, the codomain modulo the image. Is that clear? So it's just a construction. And now let me tell you what we're aiming at right now. So I just erased a whole bunch of examples of finitely generated abelian groups. So let's suppose that you had a number field and you wanted to compute the class group of the number field. It's a finitely generated abelian group. How can you quickly describe the answer? You have a program that outputs the answer. How do you describe it? Fortunately, there's a nice description, and it's called the structure theorem for finitely generated abelian groups. And here's what it says. And this is what we're going to give a complete proof of in the next few minutes. Given a finitely generated abelian group G, there are integers n1 up through ns are equal to 0, such that G is isomorphic, not in any canonical way, to the product Z mod n1Z direct sum Z mod n2Z direct sum Z mod and SZ direct sum R copies of Z. And moreover, n1 divides n2 divides n3 and so on. Divides n sub s. There's a canonical form that you can put any finitely generated abelian group in. So a class group is defined in some really complicated way. It's all these ideal modulo equivalence relation. In some reason, there are infinitely many ideals. There's an equivalence relation. You push it out, you end up with finitely many equivalence classes. So if you just sort of look at them as actual ideals, you can't see this sort of structure at all. But if you do a whole bunch of work, you can actually find always, for any class group, you'll find some list of elements that generate each of these factors. So you could tell somebody the structure of this class group is Z mod 2 cross Z mod 4 cross Z mod 12. That's the sort of answer you could give. Okay, so now let's prove this. First, as I remarked when I was just sort of talking about finitely generated abelian groups, if you take our group G right here, then you can write it as a co-kernel of a map from Z to the M to Z to the N. That is the co-kernel of a matrix with integer entries. So what I'll do is I'll just show you how to transform this matrix via left and right multiplication by invertible matrices over Z into a matrix so that it's completely obvious that the structure of the co-kernel is exactly this. And then you'll see that every finitely generated abelian group is of this form. Another thing we'll observe at the very end is that this is a unique representation. Okay. By the way, if this matrix isn't square, you can always you can always make it square by adding on some 0 columns and 0 rows or 0 rows because you can always increase n just by sending some extra elements to 0. So you can always make this matrix square. Not sure. Like that, but without loss, you can see it's square. Okay, so here's what I'll do. I'll just show you how to change bases in such a way that that matrix is a matrix in Smith normal form. Where Smith normal form following: a matrix is in Smith normal form if it looks like this. It's a diagonal matrix, so it has zeros everywhere except along the diagonal when it has entries n1, n2, down through ns, and then zeros. So that's Smith normal form. An example of a matrix in Smith normal form is 2 over like that. And yeah, that's it.
Using prior to this visibility.
Yes, just like over there. So you're right, thank you. And 1 divides n2 dot dot through ns. And s could be 0, for example. The zero matrix is in Smith normal form. So there you are, that's Smith normal form. And the theorem, which I'll prove, is that given any matrix A, there exists invertible matrices U and V, so using invertible integer matrices, such that U, A, V is in Smith normal form. Okay. First, quick question. Are U and V necessarily unique? Okay. Are they unique up to something very obvious? Probably not, because in general, well, if I ask that question in total generality, you could imagine, for example, A being the zero matrix, and then absolutely any U and V would work. So, I'm not actually, there might be some, well, there's obviously some structure. A is not the zero matrix. For example, take A to be the identity matrix, or a matrix, for example, A the identity matrix, which is in Smith normal form, then U and V have to be inverses of each other. So that's some constraint here. And since they're integer matrices, well, I'll just leave it at that. So let's prove this. And the way I'll prove it is just, I mean, it's the sort of thing you've seen probably many times in linear algebra. It's just a little, slightly more subtle. So proof, you just observe that you can transform any matrix in a Smith normal form by row and column operations over Z. So that's like the one sentence proof. I will actually explain it in more detail because, for example, in the book it's a whole page. So any A will be transformed to Smith normal form by row and column operations, so S and F, Smith normal form, by row and column operations over Z. So by row and column operations, well, row operations are just like the elementary row operations in linear algebra, except you're not allowed to divide, because that's not over Z. Basically what you want to do is you want to apply on the left or right of A invertible matrices, but the invertible condition is that it's invertible over Z, not over Q, but over Z. So if, for example, you rescale the row by multiplying by 2, that would be like multiplying by this matrix, which is non-invertible over Z. So you're allowed, most of what you do with like reduced row echelon form and column echelon form sort of at the same time. So here's why you can do this. I'll just explain why using row and column operations is enough. And just to be clear, row and column operations mean you can swap any two rows, you can rescale a row by -1, that's it, and you can add any multiple of one row to another. That's okay. So for example, this is an elementary matrix that corresponds to adding 3 times the bottom row to the first row. And this is invertible. Its inverse is 1 minus 3, 0.
Well,
Is it?
it's a row operation on one side, it's a column operation on the other
Yeah, it
side.
depends which side you do it on. That's right. So here's how we'll do this. So first, you just imagine your big matrix, 1,000 rows and 1,000 columns, or whatever, or it's 2 by 2 if you don't like big matrices, whatever. It's some matrix. In that matrix, there's some non-zero entry that has smallest absolute value. So you take that entry, and by swapping rows and columns, you make it so that that entry with smallest absolute value is in the upper left position. Okay? So that's the first thing you do. And now you take that entry, and you use it to try to clear the first row. But it won't always work, because it could be that in a situation like this. So the entry with the smallest absolute value is 2. I can use it to clear the first row, sort of, but I can't actually turn them all into 0. So clear, I just mean clear as best you can. That is, you subtract off integer multiples of this so that you make all the other entries in that row smaller than this number. And you can do that because the division algorithm, it says that some multiple of this entry minus this is going to be between 0 and 1 in this case. So in this case, you subtract off this 1 times that, and you get 2, 0, 1, 0. Okay, so you do that for the first column. That is, you have the smallest entry in the upper left, and you subtract off as much as you can, and what results is a new matrix so that the very first column, all the entries in it in absolute value are strictly less than that upper left entry. Some of them are 0, some of them might not be 0. But they're all strictly less than the upper left-hand entry. Because if they aren't, you just subtract off them. Okay? And do the same with the first column. Then either every single entry in the first row and column is 0, or there's some non-zero entry in the first row or column that's strictly less than your upper left entry. So you just start over with that entry. Swap it so that it's in the upper left corner. And you keep repeating this until the first row and column all has zeros. Okay? So any problems with that? You could definitely do it. So step 1 is to put your matrix in the form some number here, we'll call it E, and all zeros, and then all kinds of crazy stuff here. Okay? And you can always do that. Just starting from the beginning, and you choose the smallest entry and absolute value in the whole matrix, swap 2 rows, swap 2 columns, and get it in the upper left, subtract off from the row, subtract off from the column, and you end up with something here and zeros everywhere else. Okay? Now, look at the rest of the matrix. If for some strange reason there's any entry in here that is smaller than b, that's non-zero and smaller than b in absolute value, you can just repeat the same thing and you'll end up with the same picture again, but with that smaller number. So repeating that over and over again, you can do this in such a way that b is actually the smallest entry in the whole matrix that's non-zero. Okay? With b not equal to 0, minimal in absolute value.
Assuming, of course, that your matrix isn't the zero matrix in the first place.
Yes, if it's a zero matrix, you're done, so you don't have to do anything good. Thank you. Okay, so that's step 1. But actually, there's still some work we have to do. Remember, there's this divisibility condition, that n1 divides n2, and so on. So we need to make sure that that's going to happen. So, of course, we could put this submatrix in Smith normal form inductively. We just had an algorithm that did it. We can definitely diagonalize now. There's no problem. But there's no guarantee at all that these other entries, though they're bigger than b, there's no guarantee that they're divisible by b. So that's a problem. We haven't sort of dealt with this completely. I mean, if you ran this algorithm as I described it, all you'd end up with something that's diagonal, but you don't have the divisibility as you go. So if there's any entry anywhere else in this matrix which is not divisible by b, so step 2 is to make sure every other entry is divisible by the upper left entry. So I'll show you how you do that. Make sure all other entries divisible by upper left. And here's what you do. You have your matrix again, zeros everywhere, lots of crazy stuff here that's all less than or equal to b. And you have this little entry over here, which, sorry, it's all greater than or equal to b. You have this entry here which is not divisible by b. So, swap add, so these are all 0. So just add, say, a multiple of this row, say 1. So just add this row to the top. And then you end up with this matrix, B, I'll call this entry C, and all zeros, and then a C, and then zeros, zeros, and then this crazy matrix.
I think the rest of the row is not necessarily zeros. The rest of the row is
absolutely right. In fact, this could be the whole row could be anything now. So this is just, thanks James. So this is a whole bunch of random numbers, and the C right here. And the C is not divisible by B. However, just like before, you can now go and try to clear this top row, because you're really annoyed that it's suddenly not 0 anymore. So you go through and try to clear it, and what happens when you clear this position, you don't get 0, because C is divisible by B, you get something smaller than B, right there. So you end up with, over here, B and zeros, and then something right here that's smaller than B. I'll call it D.
Might not be zeros.
No, I'm actually clearing the whole. Oh, you're right, it might not be. That's true. Every single thing that is smaller than B. That's the key thing. A whole bunch of entries, zeros. Right here at D, which is smaller than B in absolute value. So a non-zero number that's smaller than B. So now I just start over way back here, and I replace, instead of getting this B to be in the upper left corner, I make sure that D here, which is smaller than B and non-zero, is in the upper left corner. And I just keep doing this, starting over every time this sort of problem occurs. And at some point it has to stop happening, because the numbers are getting smaller and smaller. Okay, so at some point it will be the case that all other entries are divisible by the upper left entry. Okay? So now we're in really good shape. So we know how to start with an arbitrary matrix, do row and column operations, so that we get in the upper left entry a non-zero, so it's not the zero matrix, a non-zero entry, then zeros everywhere, and every other entry divisible by the upper left one. Okay? Now you just repeat the same process on this submatrix. And the resulting submatrix will then have an entry here that has the property that everything else is divisible by it, and it'll have zeros. So it ends up getting something that's diagonal, and in each step on the diagonal, the entry before it divides the next entry. And that's Smith normal form. One other quick observation. Notice that when you put this bottom one in Smith normal form, or when you apply this process to it, well, if every single entry is divisible by b, if you apply left and right multiplication by integer matrices, you never change the property that every entry is divisible by b. So that's something I've just sort of swept under the rug for a minute. Okay, so I've now proved beyond any shadow of a doubt that any matrix can be put in Smith normal form by row and column operations. Okay.
Sorry, how did you get the C after the top?
Up here?
Yeah, from the last step, but C is just in some arbitrary place.
Sure. What I did was I took the row that had C in it, which starts with a 0, and it has all kinds of terrifying things in it, and then a C, and then I did the operation, the row operation, which is add that row to the first one, which is an invertible operation. And that didn't affect the B because
you already made them all zeros.
Yeah, exactly. Okay. Any other questions at all? Okay, good. So we have now proved that every matrix has a Smith normal form. And the first part of this, namely that given any finitely generated abelian group, it has a representation like this, now follows. Because think about it. You take your abelian group, you write it as the co-kernel of a matrix, and then by just changing bases, you can assume that that matrix is diagonal of this form. And now the co-kernel of the matrix of this form is just visibly has this structure. It's a group. It's generated by each of the standard basis vectors, but you're pushing it out by n1 times one of the standard basis vectors, and 2 times the next standard basis vector, and so on. So it's something like z plus z plus z, but then you're pushing it out by n1, comma 0, comma 0. The sub z module generated by that, and 0, and 2, 0, maybe that's all. So it's very clear what the structure of this result is. Okay, so now you have a handle on finitely generated abelian groups. The other thing is the uniqueness. And the amusing thing here, you kind of have to think a little about linear algebra mod P actually to do this. N1 can be characterized. I'll write this down because it really takes a little thought to believe it. So N1 is the smallest positive integer so that n1 times g can be generated by less things, like generated by r plus s minus 1 elements. So that actually characterizes n1 in a sort of an abstract way. It's just the first integer. If you take g and multiply it by 2, 3, and so on, the smallest integer, so that suddenly the number of generators you need goes down by 1. That characterizes that integer right there. And likewise for n2, that's because of this divisibility. That's the first integer because n1 divides n2, so that you need 2 less generators, and so on. So in fact, you can just read off in a purely algebraic way without looking at all how the group is presented, these integers and so on. So they are uniquely determined. However, the statement that I made here is a little bit unclear, I must admit. And I think the best way to see it, so first, observe that it's true that if you take all multiples of elements of G by n1, then what you get is, well, that's the same as multiplying each group by n1. So you just get the 0 group, direct sum these other groups which aren't, well, actually generated by, well, I mean, some of the other ones could be 0, but that's okay. But then after a while, they're maybe not 0. So in other words, the number of generators goes down. Maybe the minimal number of generators goes down, which is actually what I said here. So n1 times g requires less generators. That characterizes n1. The way I like to think about why that's true, though, is to think about taking a prime p that divides n1 and then tensoring the group G with Fp. The result, G tensor Fp, is a vector space over Fp of dimension equal to the number of factors that you have here. Then using linear algebra over the finite field Fp, you can see the statement that I made over there. I'm not going to explain that any further because I think you can think about it in your own way, that structure is unique. Okay, so the only thing that remains in the last 2 minutes is to try 1 or 2 examples. Okay, let's just do the following. I'm going to write down a matrix, and then we'll just put it in Smith normal form. So the matrix is the 2 by 2 matrix, 15, 9, 12, 6. Let's put this in Smith normal form. Is it in Smith normal form now? No, definitely not. Okay, so what's the first thing we do?
Put the 6 in the upper left corner.
Put the 6 in the upper left corner. So I'm going to do that by, I'm going to really show my steps, because it's only a 2 by 2 matrix and I have 2 or 3 minutes. So first I'll swap the rows, which is invertible. And then I'll swap the columns. gives me this. Okay, next I try to clear the first column. So I take some multiple of 6 and subtract it off there. So it looks like the best I can do is just subtracting it off, which would be 3. And then, so I'm just multiplying the first row by -1 and adding. And I'm not going to do any better than that. So,
there, or 3 12. Sorry, on the right, the 15 to 20.
Oops, no, it isn't.
Upper
just
right
minus-
corner.
The bottom right.
Oh, why did I change that? Just leave it the same. Thank you. Thank you. Okay. Yeah, you don't do anything to the row that you're adding to the other row. Okay, so let's do a little more. Now, let's clear as much as we can the first column, or the second, sorry, the first row. So we'll add -2 times the first column to the second column. So that gives us 0, and then -3 here. Okay, so now we start over. Actually, wait, we have a problem with divisibility. And also, actually, we haven't even cleared the first column. So at that point, because we haven't cleared the first column, what you do is you find something in the first column that is smaller, and then you swap that to the top. So I'll do that. So you get 3 minus 3, 6, 0. Okay, good. And now, just repeat what we did. Add -2 times the first row to the second row, which is this, and then 0, 0. That looks good.
No.
Whoops, 6. That's all right. Just didn't see the top of my 6. Okay, so now we have this. And now dealing with the first row. So I'll take the first column and add it to the second column. The first column the same, add it to the second column, I get 0, 6.
And there it
And
is.
there we are, Smith normal form. That tells us that the co-kernel of the homomorphism defined by this matrix is Z mod 3 cross Z mod 6. That's the abstract structure of that group. Okay, all right. So any questions about finitely generated abelian groups? Okay, good. All right, so the next topic will be Noetherian modules and algebraic integers. And I'll see you in Monday after this coming week.